In this video, I'm going to be going through the 2019 Trial HSC paper for engineering studies. So first of all, we have a question. What is the forming process shown in the diagram below? Well, it's rolling. So the question is it hot rolling or cold rolling? And even though we have small equiax grains here, the answer is, when we expect that because it's hot, we expect it to have large equiax grains, the answer is hot rolling. And the reason for that is because if it was cold rolling, which is what we see here with the elongated grains, it would all be elongated. It'd be cold work hardened if we had used cold rolling. Whereas those equiax grains are due to hot rolling. So that's in the textbook. I think I took the picture, maybe not directly from the textbook, but maybe something like that. Okay, which of the following stress strain graphs, this probably should have the word there, represents the most ductile material? So ductility is measured as a function of strain. So the one that has the most strain is going to be the most ductile. So that makes D the most ductile. Okay, we have a Pascal's principle question here. So the big thing, and I sometimes have a problem even when I'm writing these tests, is mixing up the areas and diameters. So you can see here that they've given us area and area. So there's no need to multiply. Normally we would square the ratio. So we're looking for the area ratio. So if we have the diameter ratio, the area ratio is going to be the diameter ratio squared. So in this case, it's 1 to 5. So what we're looking at here is that if we press down on X, because X is smaller, it's going to go a further distance relative to Y. So if we said that the piston on X moves 10, it's going to move 1/5 of that, or 2 on piston B, because it's the ratio is 1 to 5. I tend not to like questions about pushing the cylinder, the distance traveled by the cylinder. But I guess the idea we can think about is that whenever we have a simple machine, and although we don't really consider pistons to be simple machines, the idea is that we're doing the same amount of work, but what we're getting is the benefit on force we have to make up by traveling a longer distance. So in this case, we're giving a bigger force. So in order for the work to be the same, it has to travel a smaller distance. Okay, hopefully that's sufficient. So we have Gorilla Glass used in mobile phones. Which property describes the ability to withstand impact? That would be toughness. That's a pretty easy question. Which material property describes the ability to withstand scratching? Hardness. I think that's even easier. So most people are pretty familiar with hardness and toughness. I don't think that's usually a big problem with people at the HSC level, like when we get to the end of year 12 and we're looking at trials. Okay, which of the following diagrams shows alternating current? So I guess you could argue that B is alternating current, but we expect alternating current to be a sine wave. I would say, if I was going to rewrite this question, I'd say which of the following diagrams best represents alternating current, and so that would be C. This is just straight DC, and this is a half wave rectified AC signal. So this is AC that's been converted into DC, and that's done with a single diode. Okay, which of the following material testing methods is used to determine Young's modulus of a metal alloy? That would be a tensile test. The other answers of transverse beam test, Izod, and so the transverse beam test is when we bend concrete. Izod and Sharpie tests are used to measure toughness or notch impact resistance or notch toughness. And Rockwell hardness is a hardness test. Reinforced concrete consists of a ceramic composite and steel reinforcement. Which of the following best describes the properties of the two materials? Concrete is strong in compression and steel is strong in tension. C. I think that's also a very easy question. What is a likely carbon content of steel used in steel members and structural members in residential construction? 0.3% carbon. So I do think that being able to know carbon contents is, I mean, something we did in our ferrous metal handout. So it is something that I kind of expect people to be familiar with. But I try to use, these days I probably like to put in questions that have a bit more of applied knowledge. But yeah, the answer here, you should be familiar with point three. When I talk about the three things you need to know to not embarrass me, the first is that concrete is made of cement and aggregates. The second is that stress equals force over area. And the third is that 0.3% mild steel has a yield strength of over 300 megapascals. Okay, so for point six, I always like to use the example of rails, so train rails, somewhere between 0.6 and 0.8. Then we would start to say, like, I think that we have cutting blades and things like nail punches as we get into harder and harder materials. Remember that strength peaks at 0.83% at the eutectoid, and then after that, as we continue to go up, what we get is an increase in hardness. A plane's rudder controls which movement? So the rudder controls yaw. So if you think of the shark Jaws, the shark with an udder, that might help you to remember. But again, I think that's usually answered pretty well. 11, social considerations have influenced the aeronautical engineering. It's not the world's best typing there. Have influenced aeronautical engineering. Which of the following statements is most historically accurate? Jet propulsion was developed during World War I. Jet propulsion was developed during World War II. Hypersonic flight was developed during World War I. Hypersonic flight was developed during World War II. So jet propulsion was developed during World War II is the most correct answer. Hypersonic flight is when it's going substantially faster than, say, I think it's about Mach 5 is considered hypersonic flight. If you've seen the Top Gun movie, when he goes at Mach 10, that's hypersonic flight. Pitot tubes are devices used in aircraft. What is the purpose of these devices? Now, a student I think I used the same question in one of the other tests that I handed out to my students recently. And knowing what I know now, a couple of years on, I don't like this question very much, because pitot tubes actually are used to both determine the altitude and the airspeed. So generally, I would use the term the altimeter determines the altitude, but I probably would use a different question now if I was writing this test. The answer that I was looking for was the airspeed, but if you had gone with altitude, I would now mark that as correct. Which of the following is used to prevent stalling? Slats, flaps, and slots. It's going to fall. So the difference between slats and slots is that slats can move and slots don't. And they're on the leading edge or the front of the wing, whereas flaps are on the back of the wing. Ailerons control pitch. No, ailerons. I'm not going to edit it out, but ailerons control roll. And winglets reduce vortices on the wings and improve efficiency. And redundant engines are there to improve thrust more than anything, but I guess also sort of a plane can fly even if there's a plane can still fly even on one engine. Okay, the properties of some aluminium, magnesium, silicon alloys can be altered using the following procedure: solution treating, quenching, and then reheating. What type of hardening process is this? So the answer there is precipitation hardening. That's a question that I'm more inclined to use. I think precipitation hardening has seen an increase in recent years, so I think that I'm more inclined to test questions on precipitation hardening these days. Okay, so we've got an OR gate, an AND gate, and we're asking which of the following gives us correct values. So if we have an AND gate and both X and Y are 0, then we're going to get 0 here. And if we have an output of 0 on Z, we're going to have 0 here, and the OR gate is not going to work. But if we have just one value on the y, that would work, but that's not an option. We don't have anything where there's a one value where the y input is set to high or on. So in that case, we're going to need, for this to be an AND gate, we're going to need both of them to be working in order for it to work. So the answer is D. I don't know if it's required that we give you the tables. I guess that I took it from a HSC question that gave you the tables. These days, I'd probably expect you to know that without providing you with the tables. So be warned. Identify the most suitable method for preventing corrosion on a 4-person boat. So use of a sacrificial anode block is the answer that I would give. So cathodic protection is used on larger structures like pipelines. Painting the structure is used on things like bridges, and applying a protective zinc coating, well, we use that on things like zinc aluminum or even just corrugated iron. Okay, structural timber beams are often laminated rather than being one solid piece of timber. Which of the following is not true of laminated beams compared to solid beams? So, just to note that it's a not. I put that in capitals to make it clear, but laminated beams have fewer defects, so they do have fewer defects. They can be produced in longer spans. They have improved resistance to warping. I think that's fair. They have lower strength to weight ratios. So H is, and I think at the time students had pointed out that I had not reset the lettering, so that should fit better now. So the answer is actually D. So, what is the magnitude? What is the a mass of 19 kilograms rests on a surface with a coefficient of friction of 0.4. What is the magnitude of force P that's when the block is on the point of sliding? So for this, I would use the phony friction formula. And the phony friction formula looks something like pH equals mu brackets mg plus or minus PV. Now in this case, because they've given us the values of 30, well, we'll type what we normally would do is the horizontal value here is adjacent. So adjacent we use cos. So P cos theta, I'm just going to write TH because equals mu brackets mg. I don't really like this plus or minus here. So I'm just in, if I was on a Mac, I'm just going to write like that. Okay, so in this case here, because we're pushing down, we're increasing the weight of the object. So in this case, we're making the block heavier. So we're going to be adding plus PV. And so PV is P sine theta. So we've got P cos 30 equals 0.4 brackets 19 times 10 is 190 plus P cos theta, P sine theta. And so then we can say this is 0.866, P equals, do you have answers? 0.4 times, no? You didn't do this one?
I did do it.
So what are the answers? 0.5p. And then it's really important, I know that everyone's done a lot of algebra and, you know, it should be really apparent, everyone should be fine with doing this, but really make sure that you get the sign right, because I'm writing out every line, but just what we want to do is we're going to move this over to the other side, so it means we have to minus, and that is definitely something that has caused me problems in the past. 0.366p equals 76, and so that means that P is going to equal 76. We're dividing both sides by 0.366. And we get 207.6, which is D. Okay, a metal has been sectioned and etched to show its grain structure. Which of the which manufacturing process would produce this grain structure? That's casting. I think it's a pretty easy question for question 19. How many true lengths appear in either view of the hexagonal pyramid? I will not have this question in. I will not have this question in my trial that I'm making in 2022, because I said that we're not covering developments in the assessment notification. But in different years, I cover different work. So the answer is that in either view, this is fairly tough. So in the top view, we have all of these sides here are true lengths. A, B, C, D, E, and F. Like they're all true lengths. And the reason for that is because they're all shown as horizontal lines in this view here. So then we have 6 already, and then we have AO and AD. Now I can see that some people might say, well, isn't FE is shown as a true length in both? And I could see that people might come up with that answer, but because it says in either view, it's FE is a true length in both the top and the front view. So if the question said in both, how many true lengths appear in, how many true lengths are shown, how many sides are shown as true lengths in both views? Well, the answer would be FE. FE is the only one that was visible on both sides. But because we're asking in either view, I think the answer is 9. Is 8. So 1, 2, 3, 4, 5, 6, 7, 8. I think the fact that I included 9 as an option is a bit mean. But I think it would have been more interesting if I'd said included 6 and 8. I think I've made this a fairly tough question. I think the HSC question said in just maybe in just the front view, and in which case the front view is just 3. So it's AO, DO, and FE are the only visible ones because we can't see BC. BC is in the back. So yeah, the answer I want is 8. Okay, so moving on to the so this I think I've taken just straight out of the HSC, the previous year's HSC. So let's see if I can find that. Yeah, I can see. As a matter of fact, I can see someone solving this question. Cambridge coaching. But so the reactions. First of all, you need to calculate the reactions, and I'm not going to go through too much here to calculate the reactions, except to say that I don't know why they think the reactions, they have to add up to 27 total. Some of the forces vertically have to equal. Yeah, I would have just done it this way, but I guess it's just an odd line to have that here, to have the sum of the forces here. So what we're going to do is we're going to take some of the moments about A. So if we take moments about A, what we get is 15 times 2, and that's going clockwise. They've established, well, like, they haven't really, I guess they're establishing clockwise as positive, plus 12 times 3, and then minus RB times 6. And that gives us these answers. 66 divided by 6 gives us RB equals 11. If RB equals 11, we know they have to equal 26 total, so that means RA is 16. So I would just do that graphically. I would just draw. So we know that this has to equal 16, so we draw up to 16. I don't know why it hasn't gone one higher, but they've labeled it. So having had some experience with the markers, I would say that even if someone had drawn something incorrectly but labeled it, we would mark that as correct. So yeah, in this case here, they've clearly drawn it as 15, but then they've labeled as 16. Especially that there hadn't been a lot of questions asking you to draw shear force diagrams prior to this one. That's, I think, I mean, it's a sample answer, so obviously it's going to get full marks. And then it drops down. So once upon a time there was a beam that went up 16 kilonewtons. It went across and then went down 15, leaving still 1 kilonewton. It went across again, going down 12, leaving taking us to minus 11, going across again from minus 11 plus 11 gets us back to 0. And then to calculate this location here, what we can do is we can say, 16 times 2. 16 times 2 equals 32. And then we add 1 times 1 equals 33. And just to check, what we have now is 11 times 3 is 33. And that's in the negative. So if we go from negative 33 minus 33 equals 0. And that gets us back to 0. So, yeah, I don't know if they asked in the question for a label. Yeah, I don't think they asked for it to be labeled, but labeling does help. The only problem is that sometimes people had done something that was correct and then they labeled it incorrectly, and then that we have to look at. If you label it incorrectly, we have to run on the assumption that the label is what you intended. Okay, so now we have a truss. I could probably find what year this truss is, but sometimes I ask a different question. So like this question here, I've modified this question several times now, whereas yeah, with my trusses, I usually ask you to look at different points to the question. Okay, so determine the magnitude and nature of the force in CD and CF. I think they are different ones. Maybe I don't remember. Okay, so we don't need to find the reactions. It's really important here. I don't usually want you to find reactions more than once, because that would be duplicating. Then that means if you get something, if you don't know how to find reactions, you're getting punished twice. The situation here is that we can just simply cut using my notepad as the cut. I can cut through the member here. And so now I'm cutting through CD and CF at that location. And when I do that, now you can measure these, right? Everything is assumed to be drawn to scale. It says they're quite literally drawn to scale. There was a question in the I don't remember. There was a question where it said not drawn to scale. I can say, having spoken to HSC markers, that I think that even if you still just take the drawing to scale, you probably aren't going to lose as many marks as if you don't attempt it. So I don't want to go too on the record there, but I think that if in doubt, always you can. I would say you're always better off taking the drawing to scale than not doing anything at all. But typically any test that I write, I will make sure that the drawing is done to scale. So what we've got here is we're cutting through the member at this location, and we'll do CD first. So if we're finding CD, we have these two members are our distractors. And the question is, where do these two members meet? We have CF and EF. Where do they meet? At F, right? If they have the same letter in their names, right, they're going to meet at that location. That's not always apparent, because sometimes that's not going to be the case, but if they have the same letters in their names, they're going to meet at that point. So we're going to take some of the moments about F, and how many forces do we have here? Well, we have CF and EF, and they're both going to multiply by 0 because they're passing through our point of F, so we don't need to worry about them. We have CF that is 1 unit away, and we have 54, which is 4 units away from F. So it's 1, 2, 3, 4 units away from F. So our answer is going to look like we're going to have 0 equals 0 plus 0. That's for our CF and EF. I guess I could write CF, EF. And then we're going to assume that CD is pulling out from C. So we're going to assume that it's in tension. So if that's in tension, that's going to be a clockwise movement. So we're going to say plus CD times 1. and then we're going to say that the 54 is anti-clockwise. That's good. If we only have one positive and one negative, that's good. So it's 54 times 4. So because because CD is one distance away, the answer is just going to be 54 times 4, which is like 216 or something like that. 216. Okay, so that gives us the answer for, now because our answer was positive, that means our assumption was correct. We assumed this was tension, and we assumed positive. Our answer works out. Okay, and then we have CF. So in the case of CF, what we're looking at here is we have, CF, we can't eliminate CD and EF using the using moments, because there's no point where these meet. Because they're parallel lines, they will go forever without ever intersecting. So that means we're instead going to use the lone wolf method. And so what that means is we're just going to say the sum of the forces vertically are equal. So that if we know that there's 54 newtons going down, that means there's going to have to be 54 newtons going up into C. So it's going to be in compression because it's going forced into the node of C. And then because the line is 45 degrees, we know that it's going to be times root 2, which is 1.412, I think. What's root 2? Yeah, 1.4142. Okay, so if we just add that into our calculator, okay, we get 76. And we said that one was in compression. So tension and compression is the answer there. Now, I would urge you that if you have no idea how to do trusses, which is a worry at this point, you should know how to do trusses. I have told you for more than a year now that trusses are going to be a big deal, that trusses are definitely going to be in any test that I write, and they're statistically very likely to be worth multiple marks in the HSC. That if you don't know how to do trusses, the very least you can do is write tension and compression, or tension, tension, compression, compression. You're taking a pot shot, but better take a pot shot, and theoretically you could write zero force member. I do really like zero force members. This one here is not a zero force member, but it's not unlikely that I will give you a question with zero force member. I think I did in your last test. Okay, so we have a load extension graph below, represents the data collected during the testing of a steel specimen. Before testing the specimen, it was 1 meter long with a cross-sectional area of 100 millimeters. That's an unrealistic thing, but I guess I did that because I wanted the values to be reasonable. Calculate the Young's modulus, also known as the modulus of elasticity for the material. So if we look at our formula sheet, we can see that we have Young's modulus of elasticity equals stress over strain. But we know that we can use E equals Fleet. So if we go back. Okay, so if we have E equals Fleet as our formula, what we need to know is we need to know the force, we need to know the length, we need to know the extension, and we need to know the area, potentially. Or maybe not in this case. Oh no, they do, because they haven't given us stress over strains, they've given us forces. Okay, so what I'm going to do is, you can go up to this point here, but that's very difficult, much more likely to get an error if you go up to here. So what I'm going to suggest instead is that we can get a very accurate reading if we say that at 20 it equals 1 millimeter of extension. So we're going to say 20,000 units. 20,000 newtons. Remember that we always want to use newtons. We never want to use kilonewtons for any of our calculations, always newtons. When we're doing our bending, in this case here, we can give our answers in kilonewtons because we're not converting anything. But when we're converting things, we need to always work with newtons. And if we were to find the bending stress, we would at that point be converting, and we'd convert from kilonewtons into newtons. Okay, so our original length is in millimeters. We're going to do everything in grease units. We go together like megapascals and millimeters squared. Our extension is 1 millimeter. And our original area was 100. So what we're going to then have is our equation E is going to equal 20,000 times 1020 divided by brackets 1 times 100. Now, I can just divide this by 100 by taking off 2 zeros, so I can simplify that before I put it in my calculator and say okay, we get an answer of 204,000. Now remember, our answer is going to be megapascals, so we get 204 megapascals because we go together like megapascals and millimeters squared, which we can then simplify that down to 204 gigapascals. And 204 gigapascals is a reasonable value. We know that for steel, a Young's modulus of about 210 gigapascals is pretty reasonable. These days, I'm less likely to give you steel. What I will do is, if I give you a question like this, I'll give you some other alloy, just because I don't want it to be something that you can say, oh, I got an answer of, you want an answer in gigapascals, I'll give you that. But if you're doing, say, the Young's modulus of brass, say 97, lead is pretty low. Ooh, lead, it's 5.5. No, modulus of elasticity is 46 gigapascals. Yeah, okay. So aluminium 70. I'm not expecting you to memorize those. The point is that you just need to do the calculations, but it's just so that way people don't get upset when the number doesn't match it. If I get 400 gigapascals, that's possible. Yeah, it's about the same. Yeah, titanium's lower. There we go. Okay, explain why engineers... Okay, so explain 2 ways that innovations in materials used in engineering structures have improved outcomes for stakeholders. Okay, so we've said materials. Okay, so with 3 marks, we're explaining, so that means we need to have cause and effect, we need to have 2. So I guess I would give 1 mark for identifying 2, and then for each one that you explain, I would give you an additional mark. So what I would say is, okay, first one that comes to mind is concrete. Reinforced concrete is the most commonly used engineering product. I would say that the use of reinforced concrete has an advantage in building multi-story buildings in that they have good fire resistance, or because they have good fire resistance. So if we're using our cube strategy, if we want to circle our keyword, which is explain, and then we're going to underline, we want to underline 2, I know we box that. So what we're looking for, we're underlining materials and outcomes, and then we want to box 2, and then the S for ways, and then outcomes. And then E, we want to expand. Well, okay, I would think reinforced concrete, that's a pretty common engineering product. And there's lots of answers you could have for reinforced concrete. So the first thing that came to mind is, why did reinforced concrete start to become popular? Well, listening to the Sand podcast, they said that it was because of the fires after a San Francisco earthquake. The only buildings that weren't fire damaged were the concrete structures. So that's a good answer. We could also say that use of concrete reduces construction times. So use of concrete slabs has reduced the construction times for people building new homes. Then, what's an innovation in materials? Well, we could talk about steel, but I'm going to go with instead glulam, because we talked about that earlier. So we could say that use of glulam and other engineered timbers is an advantage. It allows people to use environmentally sustainable materials that can still span long distances without cutting down old growth forest or something like that. So I would write, use of engineered timbers such as glulam allow engineers to use timber in their designs without cutting down old growth forest. I would pay that as a marker. There's a whole lot of other answers we could say. We could talk about the aesthetics, right? So a lot of the time when people are using these engineered timbers, they're doing it because they think it looks good. It's often used in like showcase buildings, like universities or say Parliament houses or something like that. It's also free of defects. It allows us, I guess what I'm trying to focus on is the fact that these days we can't really use large span timber without it being engineered timber. So that's an innovation that we required. There's lots and lots of other options you could use. You could talk about pre-stressed concrete. Like I said, you could talk about steel. You could talk about the use of structural materials, steel framing in houses rather than timber. Anyway, so that's like it's not affected by termites is one of the advantages of steel framing. Okay, explain why engineers refer to shear force and bending moment diagrams when determining the effects of loads on a beam. So this actually again came from the 2014 question. Do I still have that? I do. Okay, let's see what they said. So again, this is something where I've had the opportunity to discuss this with a lot of HSC markers, and they've said the shear force and bending moment diagrams are graphical tools used in conjunction with structural analysis to help perform structural design and determine the value of shear forces and bending moments at a given point of the beam. These diagrams provide a graphical representation of the load that can then be used to assist determining the type, size, and material of a member in a structure given the set of loads without failure. For example, a steel beam design bending moment diagram can assist the structural engineer in deciding the lightest cross-sectional shape. Okay, so what I'm going to focus on is the first thing you can say is that they allow us to determine the maximum bending moment. So in a 4-mark question, this was a 4-mark question. For 1 mark, it says provide some relevant information. So if you said for 1 mark, it helps us to design the beam to ensure it's safe and fit for purpose. I give 1 mark for that. Okay, outlines the shear force diagram and or bending moment diagram, the effects of load on the beam. If you said it's used to calculate the maximum bending moment and we design based on the maximum bending moment or something along those lines, that's 2 marks. For 3 marks, you want to start adding in reasons. So provide some clear reasons of why we use it. So aside from just the maximum bending moment. So we're looking for explain. So again in our cube, we're circling explain. We're underlining shear force and bending diagrams. And then what are we boxing? Effects, maybe. The S on the effects. Okay, so we've said that it's used in designs. The maximum bending moment is typically the thing that we're most concerned about when we're using these diagrams. But also it helps us to ensure the reinforcement used throughout the entire length of the beam. So a concrete beam typically won't have the same reinforcing all the way through. It'll have more reinforcement at the higher bending moments and less, so it might have double the reinforcing here compared to throughout the whole beam. So you might design the concrete beam for enough steel to take 16 kilonewton meters. Oh, I should notice that this diagram is actually wrong. It says 32, just to show that even the HSE makes mistakes. So 32 kilonewton meters is the unit on this diagram. But yeah, you would design for 16 kilonewton meters for the whole thing, and then you'd add an extra, double the steel for the 32 or 33 kilonewton meters at its highest point. So I think that the point that this helps us with is it says we want to consider the type, size, and material. So it's possible that engineers might use a different material, it might determine what material to use. And you might say, well, if we're talking about steel, we really only use 0.3% mild steel. That's really all we use when it comes to steel. But when it comes to concrete, we can actually increase the concrete strength. So that might be a design consideration. We certainly can design for the amount of reinforcing we use or the size of a steel beam, so the size of the material. We might decide that timber isn't strong enough for a beam here. We might need to say we need to put in a concrete or timber steel beam. So that's where we talk about material type. Another thing that came up in discussions with HSC markers is we might change the design, or we might put in new supports at a different location based on that. So as long as you talked about two of those things, if you said based on the maximum bending moment, we will determine the strength of the concrete and the placement of the steel, boom, that's 2 marks. You might say we'll determine whether or not steel is required or if timber is required, that's 1, and it might determine the what sort of, if a redesign is required, that's 2 marks. So that gets us the extra 2 marks to get us to 4. Outline examples of how engineers must behave ethically in the design of the construction of structures. So when you go for, to become a chartered engineer, you have to go through an interview process. And there is a standard of ethics that Engineers Australia sets for engineers, for their chartered engineers or their members. Okay, so I have a code of ethics, and I memorized this before I went and did my interview. It's in 4 parts: integrity, competency, leadership, and sustainability. So integrity is don't lie. 2 is only design things that you know how to design. 3 is be a good boss. So don't allow people to bully the person who's different in the workplace. And 4 is sustainability. It's don't destroy the environment. Any 4 of those would be reasonable. So let's go try and give an example for each. So just go back to the specific wording of my question. Outline an example of how engineers must behave ethically in the design or construction of structures. So we can say that for our first one, which is don't lie, we should say not just don't lie, but also don't cheat, don't be corrupt. So the classic example here is, it says an example, so one example is sufficient. This is probably what I would start with. This would be like the answer I would give without having looked at that form. I would say that it's important that in the design that we don't favour contractors who we have a relationship with. So for instance, and this would be, I'd provide an example to elaborate on that for the 3rd mark. So just outline, that would be 1 mark, right? So we must act ethically in terms of acting with integrity, and I would explain what acting with integrity means. It means that we shouldn't be corrupt in our dealings with contractors or subcontractors, something like that. And I would then give an example. So it's, say for example, don't order materials from, when working on government projects, don't quote materials that from someone who you are related to, or you must declare if you're related to people, or don't receive kickbacks from suppliers. So this is actually pretty common. I don't think it's common in Australia. I've never seen this in my professional experience. That might be because I worked for government contracts where I think there was a fair amount of probity. So probity is when oversight, so people checking a lot of the time. I'm not saying that there isn't corruption in Australian engineering. I'm not saying that. I'll give an example would be, there's a lot of people who think that perhaps the redesign or reconstruction of the Sydney football stadium, the Sydney SFS. A lot of people said the SFS was fine. Why are we knocking it down to build a new one? And some people say, well, maybe they're doing that because they're getting kickbacks, because they're profiting from building a new thing. Gladys Berejiklian, she stepped down from office because there were arguments that she was using government funds to support people where she was getting a benefit from her financial support of who she gave grants to. So don't do that. That would be an example for the first one. If we looked at the other ones, how engineers must behave ethically, I just want to click back to... Okay. Practice competently. Okay, so engineers should only work on designs where they have sufficient training and experience to do so. So a structural engineer might be asked to design a water pipe, and they might say, well, okay, it's not really something that I've done. I haven't done it for a long time, but I don't want to lose this client, so I want to keep them happy, so I do the design. That might be an example of someone not working within their area of expertise. I use this answer a lot with students. When students ask me questions that I don't know, I say, look, that's outside of my area of expertise. And in engineering, it's far better that you tell people, look, I'm sorry, I don't know how to do that. That's outside of my area of expertise, than it is to design something that doesn't. Okay, the...
Chat wants to know what paper you're doing.
2019, it's on Google Classroom. I did not want that, and now my video is all wonky. I wanted this window. Okay, exercise leadership. So support and encourage diversity, make reasonable effort to communicate honestly to all stakeholders. Okay, so diversity we've already talked about. Don't pick on the person who is different in your team. Make sure that they're not being denied promotion. Make sure that they're being listened to the same way you would listen to everyone else. That's not really relevant for our design. I think that make reasonable efforts to communicate honestly and effectively to stakeholders. So if we were building a structure, let's say we were building a set of apartment blocks, and we said that we were going to be working 5 days a week starting from 7 a.m. and instead you were working 7 days a week and you were starting at 5 a.m. So that construction noise, this is a real example. I live next to a construction site that's been going for well over a year, and often I can hear construction noise on Sundays. That might be an example of someone not behaving ethically, theoretically. But communication is fairly important, and noise is actually a pretty big part of that, so that when you say that you're going to do something, meeting that expectation of what you say in your design brief. And then lastly, the last one was environmental damage. So that one's pretty important. So it's possible, an example of how engineers must behave ethically. So engineers must design their projects so in order to minimize the disruption to the native environment. An example of this would be when building an airport, you must take into consideration the native wildlife and act to protect that native wildlife. Now that can be a really expensive and irritating thing to do. So there might be a snail or a frog or a tree that you're not allowed to knock down because it's an endangered species. And if you accidentally whoopsie-daisy knocked it down, that tree that was in the way and was actually being a real pain for you getting your expensive plant in, that would be an example of an engineer not behaving ethically if they deliberately accidentally knock down the tree in order to reduce the construction time. Okay. I love this question. I've had this question in the last 3 years of papers. So I'm not saying that means it's going to be in the paper, but it's pretty likely. Okay, so we've got a people mover. What are the parts that we're going to use? So for a tire, we're probably going to use vulcanized rubber, right? If you just wrote rubber, I'll give that, but vulcanized rubber is the answer I want. The axle has alloyed steel. The property, there's so many properties we can use, but generally the one we want to use is strength, right? High strength. Remember, we're not allowed to say strong, right? In the HSC, for some reason, we're not allowed to say strong. I find that silly, but that's the way it is. So we can say high strength. High tensile strength would be an even better answer. But we could also say it has a good high strength and good toughness. So that so toughness is important because that way it can resist impact. We can also say that it's got good. Look, the fact that if they said machined, if you wrote machinability, I would feel as though that was a little bit of a weak answer, but I'd probably still mark it as correct. If you said that it's plasticity, so the fact that it can be forged, it requires plasticity to do that. That one is definitely the most open in the number of options you can give. So the light cover is acrylic transparency. The manufacturing method, I would write injection molding. If ever given an opportunity to write a manufacturing process for any sort of plastic, I would always write injection molding. But I'm sure that there are other methods you could use, but injection molding is what I would write. Okay, so the chassis is made of mild steel and it's rolled. So again, we've got steel both times. So here we might say plasticity. It means that it can be rolled, or ductility. So I guess the axle, we probably want toughness or strength. Mild steel chassis, we want the fact that it can be, it has ductility. The body panels, in fact, we have hand layup. Now, my students in 2022, we haven't done hand layup yet. We're doing in aeronautical materials next term. So we haven't done hand layup, but carbon fiber reinforced polymers, they're manufactured using hand layup. So we should be familiar with that. And copper wire, it has good electrical conductivity, and that's drawn. Is the manufacturer, how we make wire is drawing. So that's a good question. I like that one. A valve connection in a vehicle is produced by powder forming. Describe this method of manufacturing and state one advantage of this method. Okay, so powder forming is we take metal powder and we fuse it together under pressure. We then heat it, heat brackets sinter the steel in order to we're describing, so I don't know if I need to go beyond that. Yeah, I think I'd be happy with that. Powder is formed together under high pressure and then heated in a process called sintering, or just brackets sintering. That'd be enough for the 2 marks there. You could talk about that the Copeland book, which we've talked about, has a pretty good diagram of sintering and the steps. I've asked you to do that for homework, I'm pretty sure. The idea that the sintering forces it together in a cold welds it, and then the sintering process actually bonds the grains together. But what is one advantage of this method? There's lots of things we can say. We can say that we can powder form metals that won't alloy. So, for instance, if you have something like a copper tungsten, we can't make a copper tungsten alloy, but you might need something with a lot of conductivity and a lot of hardness. And so you can't. You might use a copper tungsten powder formed object rather than because you can't use a copper tungsten alloy. That would be an example. You can also have self lubricating materials because it's porous. So you just write for one mark. You can write because powder formed objects are porous, they can be self lubricating, which means that rather than having to take the thing apart to lubricate, we can just apply the lubrication to the outside and it will move through the object because it's porous. We can also say that it typically has very high finish, so it doesn't require additional manufacturing. So that's one advantage. A disadvantage, they haven't asked for disadvantages, but if they had, you might say that it typically has lower tensile strength than if it was machined. But the fact that it doesn't need any machining is a big advantage. Okay, the gears in a vehicle have been hardened and tempered. Describe the process and the resulting grain structure, including a labeled diagram. Okay, so describe the process of hardening and tempering. First of all, we heat to red hot or 100% austenite or 100% gamma steel if you don't want to spell austenite. Remember, it's red hot, 10 out of 10 hot. And then we're going to cool rapidly by quenching in oil, or in oil is fine. Right, we're going to heat to red hot, or heat to 100% austenite, or heat to 100% gamma steel, then quench rapidly in oil. That's sufficient for the 2 marks. You've described the process. It does say describe the resulting grain structure. The resulting grain structure is acicular or needle-like grains. And if we want to find a picture of that, we'll type in. Okay. Well, I like this picture. So just draw a lot of sticks like that. Just lines in every direction is how we draw a circular martensite. If you just draw lines in all of these directions and then write a circular martensite, that's all I need. Now, when I've had this question in the past, people have said, what's the difference between tempered... Oh, I said tempering. Oh, I only talked about the hardening process. I didn't talk about the tempering process. I would have lost marks there. Okay, for 2 marks, heat to 100% austenite, then quench rapidly in oil, then reheat again at a lower temperature. I'm going to add for some amount of time, but just a lower temperature, right? That's all you need to write. I forgot to write about the tempering. But when I drew my diagram, I came back and remembered, I have to talk about tempering because I want to compare the difference between tempering and just quenched. Quenched steel and tempered steel both look the same. There's no noticeable difference between them. What happens is that microscopic amounts of graphite form in the tempered steel, which you could add, but I mean that would really be going above and beyond. Make sure you label the diagram. You will lose a mark if you don't write a circular martensite. Okay, the following image shows 2 bicycles, a bicycle produced in the 19th century and another produced in the 21st century. Justify 3 improvements in the production between these 2 bicycles shown. So I would say something like pneumatic tires. I would say tube steel and chains. Yep. So we want to justify the 3 improvements. That's the use. So for first mark, I would say the use of chains allows the rider to use mechanical advantage to help them go faster and to deal with steep hills. The use of tube steel drastically reduces the weight of the bike, allowing riders to go to travel at faster speeds. And the use of pneumatic tires made of vulcanized rubber provide much better comfort and I'd say also better grip. So better ride quality and probably better traction. Okay, so I think that's sufficient for 5 marks. Evaluate the environmental impact of the use of bicycles for transport. Now I've asked for 5 marks here. Keep in mind that if we're cubing this, we're starting with circling evaluate, and then we're underlining environmental impact of bicycles. I don't think we need to box anything. And okay, so what are we going to say? Well, evaluate typically means we have to make a judgment, right? At the end of it, we have to make a call. We have to say if it's good or bad. Now, evaluate doesn't mean that we ignore the negatives. And if anything, we should actually include the negatives. I would recommend for 5 marks, you want to include negatives. So what would I write here? I would say the positives of bicycles include the fact that they require much fewer materials than other modes of transport, such as motorcycles and cars. Also, they don't require fossil fuels for engines. Instead, they are driven by human power. Because of this, they have a minimized reliance on non-renewable fossil fuels, and they reduce the carbon dioxide emissions. The negatives, however, they still do rely on some amount of non-renewable. So they do rely on some amount of materials that need to be extracted from the earth. Although materials like steel can be recycled and often are recycled, the recycling process still requires some amount of energy, which requires CO2. In total, though, bicycles are far more environmentally friendly, or they have a much reduced environmental impact compared to motorcycles. That would be the answer I would give, something like that. Now, I dare say that what I wrote there probably wouldn't fit on all those lines, because it's worth 5 marks, but compared to, so I'll go another time just to see if I can shorten it. So compared to motorcycles, bicycles don't rely on fossil fuels to be powered. This reduces their carbon dioxide emissions and their use of non-renewable resources. They also require less raw materials. However, they do still require some amount of materials and machining, and even if these materials are recycled, this will still have some CO2 impact. Nevertheless, they have a lower environmental impact than motorcycles. That would be what I write, and I think that can fit on those lines. Okay, this question, I think I've used this question like 4 times in a row. I like it because it's fairly simple. It's a nice clean question which asks about a thing that we see relatively frequently. So what I want you to do is I want you to calculate the mechanical advantage, the velocity ratio, and the efficiency. So these things are all given on our mechanical advantage is load over effort. Velocity ratio is distance traveled by the effort compared to the distance traveled by the load, and efficiency equals mechanical advantage over velocity ratio. So if we go back to our question, okay, calculate the velocity. Okay, mechanical advantage. So the effort is always where the engine goes, or where the human if there is no engine. So in this case, the engine or the human is the 450 newtons, and the load is 70 newtons. So we can straight away say 450 divided by 70. I would show the working out is 6. Oh wait. Now I know that load over effort. I know that my answers for these bikes should be an answer less than 1. So load over effort. We said the load is 70 and then the human is 450, which is what I said, but it wasn't what I typed in. So I've got 1.55. Typically we go 4 decimal places. So mechanical advantage equals load over effort. We said that load is 70 and the effort, which is the human, is 450, which equals 0.1555. We could round up to 6, but anyway. Okay, the velocity ratio is the distance traveled for the effort divided by the distance traveled by the load. Now, what we need to think about here is how many times we said the effort is the human. So how many times is the pedal of the human going to travel around, and what is the circumference of that going to be relative to the circumference of the wheel? And we've also got to remember that the big wheel is going to turn around multiple times. The idea here is that when this has gone 20 teeth, the pedal will have only gone 20 teeth. So the pedal won't have done a full rotation. And by the time the pedal has done a full rotation, we'll have done 20 teeth, 20 teeth, 10 teeth. So we'll have done, this big wheel will have done 20 teeth, 20 teeth, 10 teeth. The big wheel will have traveled around 2.5 times. So the load is going to be multiplied by what we call nrev, right? The number of revolutions, which we say is 2.5 times, right? Or 50 divided by 20 if we wanted to do that. But I'm just going to say, I know 50 divided by 20 is 2.5. And then we're going to talk about, okay, what is the circumference? Well, so the circumference is 700 pi. And the circumference traveled of the pedal is 170 times 2, because it's a radius, not a diameter, times 2 times pi. Thanks. Now, because we have pi on both sides, we don't need the pi. So what we get our answer is then we get 340. I did that in my head. 1400 times 730. 700 times 2.5 equals, yeah, that sounds about right. 1750. And then we're going to say 340 divided by 1750 equals, oh, whoops. $340 divided by 1750 equals 19. So equals 0.1943. Now you'll notice that I just typed the wrong number there. I think the markers would be pretty reasonable there, that they would actually see, oh, that they would actually get their calculator out and they would actually check to see if what you had done is just made a mathematical error. They would say, well, the working out looks good. I'm not sure what they've done here. And there is an expectation that a marker should actually get the calculator out and do that work. Okay, so 0.155 divided by 0.1943 equals 80%. This question, I use this question a fair bit, so yeah, I sometimes see actually students just write 80%. I probably need to change the numbers next time I use it. Okay. Okay, a vehicle travels at constant velocity of 12 kilometers per hour on a level path. The power required to maintain this velocity is 300 kilowatts. Calculate the resistance to motion. Okay, so if we go to our formula sheet, it wasn't always on the formula sheet, but it is now, that power is equal to fight the power F. Oh, it's not on this formula sheet. It is now, but fight the power FV. We know that S divided by T is velocity. So displacement divided by time is velocity. So power equals force times velocity. I remember when I first started teaching, I got really stumped by these questions because I just didn't know, like, how do I find the velocity? You know, how do I find the distance and the time traveled? So that's why I came up with that mnemonic. Okay, so what are we doing here? Well, it's a pretty easy question, really. What we are being asked to do is we say that we know that power equals force times velocity, which means that force equals power divided by velocity. Right, that looks right. And then we're going to say that equals power is, remember, we always want to use base units, SI units. So 300,000 divided by, now we can't use 12 kilometers per hour. What we're going to do is 12. And some of you may have heard me talk about Ed Sheeran and how he has an album called Divide. He also has albums not called Divide, which is confusing. But I always think about, we're always dividing by 3.6. So we'll do the 12 divided by 3.6 first, because I don't have the world's best calculator here. 12 divided by 3.6 equals 3 in a repeater. And if I do divided by 3, that'll be, we get 3? Yeah. Let me just check. 300 divided by 3.33. Yeah, no, that's much better. 90. But it's 90 kilonewtons, right? Because it's 300,000 newtons. So yeah, 90 kilonewtons, or what you should be writing is 90.009, something like that. Okay, a vehicle with a total mass of 1,200 kilograms and is stopped on a 20 degree incline. The coefficient of friction of the tires is 0.25. Determine the force of the engine required to pull up the incline. Okay, so for this we're going to be using the too many guys formula. So T equals mg brackets. Now it's sine plus or minus mu cos. Okay, so we can expand that out. We can say T equals mg sine theta. And in this case, because we're pulling it up, friction is not our friend. Friction is going to increase the amount of tension on our rope this time. So we're going to put in sine 20. So it's going to increase. If we were just trying to keep the boat stationary, right, where the cable was just holding in place, in that case, friction's our buddy. Friction is reducing the tension. But here, if we want to pull the rope up, now tension is being a jerk. So we got mg, I usually write mu m dot mg dot cos theta. Okay, so what do we have now? We're going to say mg is 1200. Sine 20 plus mu, which is 0.25, brackets 1200 cos 20. Now, I do like using just the too many guys formula, but I use the expanded formula because when you look at HSC answers, they're typically going to use the expanded formula. So that's why you want to be familiar with that. Trigonometry is what we're going to need. Okay. What we'll do first is we'll do sine. No, we have to do 20. Okay. And then cos 20. Okay, 9397. Okay. So now, because I've already got the cos number here, I'm then going to multiply that by 1/4 of 1200, which is 300. Times 300 plus 212, and then here we're going to do 1200 times 0.342, which gives us 410. And then 410 plus 28 equals 692.4. Okay, that's the answer I have. I didn't multiply everything by 10 because of gravity, silly gravity. That's even why I write MG, is so that I don't make those mistakes. Yeah, okay, that number seemed low. So this is where estimation is important, but you guys probably don't have the experience to say, well, that number seems low. But typically, you know, if you're pulling a car or a boat or something like that, something that weighs a ton, if you're pulling it up an incline, you need a fair bit of force. Okay, so I feel better about that answer. Tell me if I've made a mistake in the comments. Okay. Polycarbonate sheet is used in a vehicle. The sheet must resist a load of 300 newtons when tested with a 5 by 5 millimeter punch. The allowable shear stress in the material is 10 megapascals. Calculate the thickness of the sheet. So this is a ribbon shear question. I'm just going to keep this because I don't have any answers, so I'm doing this blind. Okay. So a sheet must resist a load of 300 newtons and tested with a 300 by 300, by 5 by 5 punch. Okay, so first of all, you need to know that stress equals force divided by area. Okay, so what we're doing is we're calculating the area is what we need to do. So that means that area is going to equal force divided by stress. That seems right? Yep, okay. So what we're going to do then is we're going to say the force is 300 newtons and the stress is 10 megapascals. We're using the Greece unit, so we go together like megapascals and millimeters squared. So that gives us an answer of 30 megapascals, 30 millimeters squared. Seems about right. Just checking. Stress is 300, and force is 300, stress is 10, gives us an answer of 30. Okay, and so then our area is going to be, well, we know that the punch has a perimeter of 5 plus 5 plus 5 plus 5, which is 20, right? 5, although 4 times 5 is 20. So thickness equals, because we're going to calculate the ribbon area, this area here. So we know the area of this internal ribbon is going to be 30 divided by 20. It's going to give us the thickness. $30 divided by 20 is going to be 1.5. 1.5. Okay. Okay, so we've got a drawing here. Now, if I knew exactly what year, you know what? I could find the answer. I could do that. Things I can't really edit. I can't pause easily.
Are you posting the VOD of this?
Sorry?
Are you posting the VOD of this?
Yeah. Did someone ask?
Yes.
Yeah. Yeah, I will eventually put this up at some point. Maybe what I wrote actually is exactly the wording. Completely assembled orthogonal sketch of the door hinge. Oh yeah, great. That should be enough to find it. (2012) paper, and then we can go to the answers. I think I went to the paper, not to the answers. Sorry, marking highlights. There we go. Okay, so it saves me having to draw it. Okay, so what are we looking for? It's, how many marks is this? 5 marks. Yep, it's a pretty reasonable expectation for 5 marks. Okay, so do we want to have both side by side? Okay, well, just first we can see that the countersink of 45 degrees. That's where we get our thread started. We can see it's fully threaded. All the way down this screw is threaded all the way along. At the end of it, we're going to have a nut. Remember, we don't section nuts, or we show nuts as shown here. Now, it's worth pointing out that these days, you would not be expected to show a nut with a curved top like this. These days, you would just show it as a rectangle with the lines. Remember that these lines for the flat face, I guess, of the hex nut, that should be between the threaded section. So we can see here we've got our countersink and then we've got our threaded section. We have a sleeve. So can we see the sleeve? Yep, there's the sleeve there. 13 is the outside diameter. That's what OD means. Now, we don't section washers. Even though we're going through washers, we don't ever section washers. And we can see here we've got a double washer here. So that's why we don't show that. This thing here, this bolt, I guess, which with the Allen key hex nut, let's say it's an Allen key threaded section, they haven't asked us to section that. They've only asked us to section the door hinge. Oh, okay, sorry. Yeah, if you scroll down, it's already shown for us, so we don't need to draw that. Nice, thank you. Okay, so It's good drawing. I think it's pretty fast. You should be able to do this pretty quickly because it just wants you to understand that you don't section washers, that you'll lose marks for not showing bolts. Now, the thing I'll point out here is that there really should be a difference between your line weights. So I should be able to tell a difference between your thick dark lines and your thin dark section lines. And I can't see that in this diagram. So that's something that I would point out. So if I was looking for 5 marks, what would I be looking for? First of all, you need to draw both bolts, right? The bare minimum, you need to draw both of these, or both of these screws, both of these threaded components. That's 1 mark. The second mark would be drawing the hex nut appropriately. Now, they don't tell you the thickness of the nut. If you remember that I talk about head at 7, nut at 8, that the thickness of the nut is 0.8 of the diameter. So if they've said it's an M10 bolt, this is 0.8. Now, would I can tell you that I would never be getting a ruler out to be measuring whether or not that was done to the right size, whether or not this was actually 0.8 of the thickness, as long as it looked close to reasonable. If you had done 0.7, if you'd done 0.9, I would personally be giving it correct, because the markers just don't have time to scrutinize the papers when they're marking digitally. If it was me, I would have had a half or a third of the sectioning that these people have had. There's just way too much sectioning, and that takes you time to draw those lines. You don't have that time, so you don't need to draw as many lines. I like that the lines are drawn parallel, so that's good. Nicely done there. You'll notice that, so first of all, one point just for drawing the section. Second mark for drawing the hex nut. The third mark would be for drawing the sleeve, and then after that I would be looking for the sectioning, right? So both types of sectioning. I'd probably give half a mark if it was just either type of sectioning, and then the thread. The thread is drawn appropriately is half a mark on each. And I want to see that you've terminated the thread appropriately here, that you've drawn this corner at the end of the thread. If you aren't familiar with that, one of my earliest videos talks about how to draw threaded sections. So yeah, I think it's a pretty good drawing. Yeah, I think I may be given too many marks there. So we'll say it's half a mark for this, half a mark for this, half a mark. So that's, we'll count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that would be my 10 marks that I would be looking to give. Okay. Aeroplane propellers produce thrust. This forward movement combined with the shape of the wing, the aerofoil, produces light lift. In the with the aid of the diagram in the space below, explain the physical cause of this lift. Let's just draw, let's say that this is our wing, right? The idea is that air moving over the wing creates an area of low pressure above the wing and high pressure below the wing. This difference in pressure generates lift up, or perpendicular to the direction of the wing, as a matter of fact. What was that, 3 marks? So as long as you've drawn the wing and you've drawn air above and air below, so let's say you've drawn the wing, let's say you use this whole picture, but let's say we drew this wing, we said low pressure, high pressure, and you then drew lift perpendicular to the wing. I would say that was a sufficient diagram. And then in your diagram you say that because there is lower pressure, the movement of the air over the wing creates a low pressure above the wing, a higher pressure below the wing. The difference between these two pressures generates lift perpendicular to the wing. I would be happy with that for 3 marks. You could talk about other aspects. We've talked about how we generate lift, and we've talked about how it's really quite complicated. There's conservation of mass, energy, and momentum. But if you just write conservation of mass, energy, and momentum on its own, I can only give you 1 mark. I can't give you full marks unless you build up to that by explaining that because the air is traveling over the wing faster than the air below, it has a lower pressure. This lower pressure generates lift. Or you can talk about because more matter is hitting the bottom of the wing, that generates lift. Or because we can say that the air acquires a downward direction, the conservation of energy means that the wing has to be pulled up. Okay, determine the magnitude of the lift in this question. So these questions, effectively what we're drawing is, and I don't really like to use paint too much, but we're drawing a right angle triangle, and what we're going to draw is weight is always down, vertically down. It's the definition of down. It's the definition of vertical. And then we're going to have lift, which is perpendicular to the wing. And then we're going to have thrust minus drag. Okay, so our angle of attack is 19 degrees, which means that's 19, which means I'm not going to do the maths, but you have to take my word for it that this part here is also 19. So if we have a triangle that, okay, is there a shapes? There is. I really want to draw it the other way around. Okay, if we have a triangle that's 19 degrees and we know that our weight is the hypotenuse, the weight is 85 tons, so that should be enough to get us started here. So let's, okay, so our mass is 85 tons, so it's 85 times 1,000 times another 10 for gravity, which gives us that. Okay, excuse me. So, determine the lift. Oh, easy question. I can't believe I made that 2 marks. That's a very easy question. It was very, feeling very generous on that day. So what we're finding is on this diagram that our lift, if this is 19, our lift is adjacent to that 19 degrees. So we can say lift equals so cos 19, and we know that our answer has to be pretty close, like it needs to be above 6,000 for instance. So we've got, we're just going to use kilonewtons because I don't want to type in the 1,000. I'm more likely to make an error. I'll go to 19 cos first. 19 cos times 85 803 kilonewtons is the answer there. Okay, aircraft X and Y have different shapes. Explain how the shape of the aircraft affects lift and drag. So it's an explain. So in our cube, we need to circle explain. And we know explain means cause and effect. And we're going to underline shape and lift and drag are the key things that we're looking for. So what we can say is that for aircraft X, there is a much bigger surface area of wing, and it extends further out. With this is going to generate more lift, but it will also generate more drag. Whereas aircraft Y will generate proportionally a small amount of lift, but a much lower amount of drag. So just so I can check, because I'm not writing these things down, I'm just saying them out loud. Explain is cause and effect. So we're saying because the aircraft X has proportionally more surface area, and that surface area is extended further from the fuselage, it's going to generate more lift but also more drag. Aircraft Y is going to generate less lift and more drag. The reason why we do this is so that aircraft Y is going to travel at much higher speeds, where drag is much more important. Okay, aircraft typically have a lower factor of safety than structures. Explain why and how engineers apply a low factor of safety for aircraft. Okay, so explain, we're looking for cause and effect. In this case, we're going to say that because aircraft are regularly inspected and maintained on a very thorough schedule, their problems are identified much sooner than they would be for structures. As a result, also, in order to reduce the cost of travel and the environmental impact of travel, having a lower factor of safety reduces the cost and environmental impact of travel, but this is compensated for by more frequent inspection, testing, and maintenance schedules. Okay, I think we're in the home stretch now. Telecommunications. The question below depicts a signal transmitted using 3 different methods. For each, identify the type of modulation, one advantage of this method, and one application. Okay, so the first one here is FM. So we can see that the frequency has been as varied. So we can write down frequency or FM. I will mark both of those as correct. The advantage of frequency modulation is that it's not affected by electrical spikes, and it can have better quality audio. Right. So if you write advantage, better quality audio. An application. Transmission of analog radio and analog TV signals. These days we don't really have any analog TV, but FM is still used for commercial radio. Okay, now we have AM, so we can see that the amplitude or the volume of the wave is increasing and decreasing this time around. And so what we're going to say here is that the advantage of AM is that it has much further distance. So its application, emergency broadcasts are usually done on AM radio because it goes further. And then we have phase modulation. If you wrote PM, I would still mark that as correct. An advantage of phase modulation is because it's transmitted at higher frequencies, we can typically send more data, so it has higher bandwidth. Also, it's not affected by the Doppler effect, which is important when we're sending things to satellites. We don't want to. It doesn't matter if the frequency gets distorted by the Doppler effect, and it doesn't. It also is not affected by amplitude spikes like AM. But I would generally say higher bandwidth is a good answer. Application: Wi-Fi signals, digital radio, Bluetooth, satellites. Okay, explain 2 advantages of optical fiber for telecommunications. Okay, explain. So remember, we've got to talk about cause and effects. We're boxing the word to and the S of advantages. We need to have explain 2 advantages. We're underlining optical fiber and copper wire. So what are 2 advantages? Well, the first advantage of optical fiber is that it has greater bandwidth. It can carry more information for the same for a lower cost. That would be the first thing I would say. Then you can also say that it has less attenuation. Okay, so we need to explain this. So because of the speed of light, because optical fibers transmit information at the speed of light, they can transmit more information faster. Also, we can say because optical fiber transmits its signal using infrared light, it also is less affected by attenuation, so it doesn't need boosters. It doesn't need stations to add more energy into the signal to keep it going over long distances. It also offers additional security because light can't be detected from outside of the cable, unlike copper wire, where the electrical signal can be detected and listened into by sophisticated parties like spies. So I think that's fine. I think we've explained why, and we've talked about 3 different reasons. You only need to use 2. I probably would go with attenuation, but I do see people talk about security, that it's a closed loop. You can have a optical fiber line that is totally secure. Okay, describe 2 electrical components that use semiconductors. Now, it's really important here that the word is describe. So we're circling the word describe. We're boxing the word to. We're underlining semiconductors. So what are 2 components that use semiconductors? Well, the two classic ones that we use are diodes and transistors, but that would be identifying. You'd only get 1 mark for that. Because it's describe, you need to describe it. So we'd say diodes are used for rectification of AC to DC. That LEDs are diodes that provide light, and we can also say that LEDs are used and component to ensure that, like, they're used in radios to ensure that to demodulate AM signals. Describe 2 electrical components that use semiconductors. Okay, transistors are used as switches and amplifiers. I would focus on the switches. Transistors contain 3 layers of semiconductors that can be used as a switch, and these switches make up the basis for modern computer chips, for logic gates, which make up modules, which make up the basis of modern computing. And that's the end of the paper. Okay, so that took about an hour and a half. Hopefully that was beneficial to some of you. I'll keep the video up on Twitch. I will check it before I put it up on YouTube, but I'll probably put it up on YouTube at some point.